Okay, so it's my pleasure to welcome Bill to talk today about the lookup conjecture and rational smoothness in type A2 tilde.
Okay, well, thank you. So this is joint work with Brian Boe, who, as many of you know, he just retired, and so I invited him to give this talk instead of me, but he declined. But this has to do with some stuff that's really a continuation of some work that Brian and I began a long time ago. And so I'm giving this slide talk for two reasons. One is there's some pictures I need to show, and the other is that I'm going to the AMS meeting in Mobile in this week, and I need to prepare slides for that. So but anyway, so let's just get started. Except I don't know how. Okay, I guess I have to click with them. I don't know how to go back with this. But do you, I mean, can I only use there? Oh, I see. But I clicked. Okay, it wasn't. Okay. So anyway, this is just the general blurb at the start is Schubert varieties. I'll say a little bit about what they are. Probably most of you know something about them, but they're quite important in representation theory and geometry. And Carrell and Peterson, made a very famous paper where they highlighted the local topology of Schubert varieties at torus-fixed points. And so this is simplistic points which are rationally smooth, and the goal of this work is to understand the rationally smooth locus in Schubert variety. Now, understand means really to sort of describe in a kind of a conceptual way. So in the sense it can be calculated. But so the general setup is this notation. So G is going to be a simple, which we won't really need most of it all, but just to say what things are. G is a simple algebraic group or a Kac-Moody group, and B and T will be a standard Carrell subgroup in maximal torus. W is the Weil group, and this will all become very concrete in a few minutes. The Weil group equipped with this Bruhat order. L of W is the length of W, and the flag variety is G mod B. Sitting inside there's a Schubert variety, which is G mod B, which is the union over all these X that are less simple to W in the Bruhat order of these B, X, B. Now, in the case at hand, G mod B might be an infinite dimensional flag variety if we're in the Kac-Moody setting, but the Schubert variety is nevertheless a finite dimensional projective variety of dimension L of W. Now, what does rational smoothness mean? Many of you have seen this before as well, but a variety is rationally smooth if informally, if its relative homology groups X, X minus X look the same as if it were a smooth manifold. And so that's the formal definition is a displayed equation, but just think it's a smooth manifold. No, I think it's only I think it's rational smooth at the point if this is true. It's this relative homology at that point. I believe that's the well, I think this is right, but it's possible. And in any event, it won't. The precise definition we're never going to use, so it actually doesn't matter. But I think this is actually right.
Sorry, can you find an easier to discuss about that? So it doesn't. Your group doesn't depend on the isogeny at all.
No, because it's the flag variety doesn't detect the isogeny type of group.
Okay, thanks.
So in any event, we want to understand, given a W, what points X are the rationally smooth? What torus-fixed points are the rationally smooth? And in the end, this problem is going to be reduced to a very combinatorial kind of problem. But let me just say a little bit of the background. So Carrell and Peterson, where their work comes in, is they define polynomials Pwx of Q in the variable Q. Q is unfortunately a little overused in this talk, but it's too late to change now. But these polynomials detect rational smoothness because X is a rationally smooth point if and only if this polynomial is the constant polynomial 1. Here, W and X are elements of the Weil group. And this has some consequences in representation here. Now, the Carrell-Peterson polynomials can be calculated, so in principle, it's possible to tell if any point is rationally smooth, but it's a complicated algorithm, and it's not so easy to use to prove anything about the collection of points which are rationally smooth. And so Carrell and Peterson provided an alternative test for rational smoothness, which is much easier to describe. So I'll describe that now. To do this, I have to define some integers, which again, unfortunately, we chose the letter Q. This is not the only, yet we're not done with Q, but these integers QWX. So if we take two elements in the Weil group, so again, so the Weil group you can think of as like the symmetric group, where it's going to be a group of an affine symmetric group. The reflections are like the transpositions. If X is less than or equal to W, there are at least the length of W reflections such that Rx is less than or equal to W in the Brouwer order. And geometrically, what these reflections correspond to T invariant curves, torus invariant curves in XW passing through X. There have to be at least the dimension of XW such curves. And what we're going to do is, and that's this geometric interpretation of Dyer's statement. And what we define QXW to be the excess number of T invariant curves. It's the number of reflections above the minimum of T invariant curves that go through that point. So it's a non-negative integer, and we can illustrate it on the next slide. So this is a very simple slide. So this is a slide probably many of you have seen before. It's the Brouwer graph for A2. And the main point to illustrate this is, so you've probably all seen this. There are the 6 elements here. These edges here in the graph are the reflections, are when 2 elements differ by a reflection. And the height of an element here is its length. So let's look at what Q is for the element W equals S1, S2, and X equal S1. So S1 is less than S1, S2. So let's calculate the Q. Well, there are 2 reflections from S1 that stay less than S1, S2. Namely, I can go down via S1, or I can go via this reflection S alpha tilde. So there are 2 reflections, and the length of W is 2. So therefore, Q is 0. QXW is 0 at this point. And in this simple picture, QWX is 0 for all pairs X less than or equal to W. You need to go to S4 to get some pictures where that's not the case. Okay, so are there any questions at this point? Is it sort of clear what these key integers Q are? So Carrell and Peterson proved the following theorem, which is that, and I'll state it in terms of non-rational smoothness. So XW is not rationally smooth at X if there's some Y in between X and W where the QWY is positive. There are too many curves. So the way we think about it is that if it were smooth locally, it would look like a vector space. And the vector space would be the dimension of the manifold. Every T invariant eigenspace would be a T invariant line, and those would be the T invariant curves. So the excess number of curves is in a sense measuring the singularity, or a kind of related to the singularity. Now it turns out it's not enough to check that QWX is 0. There might be the correct number of curves going through X, but it could still be singular. And in that case, what would happen is that there would be too many curves at some Y in between X and W. So this is a very conceptually easy test. And the drawback is that to see if XW is rationally smooth, you have to calculate QWY for possibly a very large number of Y. And so Brian Boe, many years ago, made this conjecture, which is verified using GAP, and it's the following. It's what we call the lookup conjecture, which is that to test whether X is a non-rationally smooth point, it's enough to check that either QWX is positive or QWY is positive, where Y is connected to X by a single reflection. So in this picture, here's the X right here. The Y's that are connected to X are these ones that are marked in red. And to test, so according to the lookup conjecture, to test whether X is rationally smooth, we would only have to check Q at these 4 points here. Whereas the Carrell-Peterson criterion, we would have to check the Q at all the yellow dots in between W and X. So this would be, a drastic simplification because there's never more than, the rank of the group reflection, or well, not the number of positive each reflection. So, and in any event, it would drastically reduce the amount of checking that is required. And so there's a lot of evidence for this conjecture, I would say. We checked it in classical types up to rank 6. In fact, in this picture here, there's an error edge where you have to go up by length 3, say, but in reality, in the classical groups, it appears that it's enough to only go up by length 1. However, in the group F4, there's exactly one example where you have to go up by length 3. So that's a little bit weird. In type A, the group GLN is much simpler. XW is a non-rationally smooth at X, if and only if the bottom vertex has a Q positive. So that type A is much simpler. And we refer to this case as the non-trivial case of the lookup conjecture, where you're not rationally smooth. The difficult case is where you're not rationally smooth, but Q is 0 here. That's the hard case, because then you have to find a Y where the Q is positive. If Q is positive here, then it's an easy case. So we call that the trivial case of the lookup conjecture. Okay, so in type A, only the trivial case of the lookup conjecture occurs, but this is not true in other types. And Brian and I were able to prove the lookup conjecture for certain File group elements corresponding to certain Gmod. They correspond to Gmod P, where P is a maximal parabolic. So the precise statement was that the lookup conjecture is true if G is a classical semi-simple group and X and W are maximal coset representatives of WP, where WP is a maximal parabolic subgroup. So for exceptional types, this also holds, except at the time when we did it, E8 was out of reach of our computational ability, so we couldn't do that. And the proof is actually combinatorial, and it's got a kind of interesting feature to it. I mean, the strategy is that, you know, if X is not a rationally smooth point, but Q is 0, you want to find a direction where you can go where Q is positive. You have to kind of try to identify this direction. But to identify this direction, we had to show that we could only identify this direction in certain settings. So we had to prove that certain settings could not occur in the Q equals 0 setting, in case Q is 0. So the way that was excluded was that we could say that if certain configurations occurred, there would be an element Z where QWZ was less than QWX. And so if QWX was 0, we could exclude these configurations. So it was an interesting feature from my point of view that the positivity or the non-negativity of these Qs entered into the proof. And although the proof is purely combinatorial, the positivity of these Qs was not something that was accessible to our methods. So it was kind of an external ingredient. So, you know, I thought that was probably the most interesting part of the proof. Okay, so anyway, after this, you know, it was the lookup conjecture, not the lookup theorem. So I've continued to be interested in it. So with Wenjing Li, we began to investigate the lookup conjecture for affine file groups. Now, these are infinite groups. So since we were unable to prove it for these finite groups, it may have appeared to be foolish to look at infinite groups. But the reason was, in fact, that I thought that in type AN tilde, this infinite group, it would be like AN, and that only the trivial case of the lookup conjecture would occur. And so the first thing we tried to do is to prove that in type AN tilde, that would be just the same as in type A. However, we failed. We tried for a little while and failed to prove this. And I happened to run into Sarah Billy at a conference, and I mentioned this to her, and she told me that she knew that this was false. Send me an example. So that kind of punctured this balloon. But what it turned out that in a sense, the lookup conjecture was almost true. I mean, the initial guess was almost true, because we conjectured that the initial guess was true except for a certain family of file group elements. So unless W was what was called a spiral element, what we call a spiral element, we conjectured that only the trivial case of the lookup conjecture would occur. So we did not prove this conjecture, but we decided nevertheless to look more closely at the spiral elements, since they were the ones which had the behavior that appeared to us to be the most interesting at the time. So let me just give you a couple of slides where I explain the affine file group of type A2 tilde. I'm going to show another slide which will look very similar to the one I'm going to show now, but a little bit different. So the way I'm going to realize the affine value, R2 is going to be the subspace of R3 where the sum of the coordinates is 0. And in there we have three elements here, alpha1, alpha2, and alpha2 alpha tilde, which you may recognize as the positive roots for type A2 for SL3. So we can, given one of these roots, or given any data actually, we can define a line consisting of the elements whose inner product with beta is n, and we can define S beta n to be the reflection across this line. oops, I went ahead a little bit, but these lines where beta is taken to be one of these alpha 1, alpha 2, and alpha tilde divide the plane into small triangles, which are called alcoves. And the affine Weil group is the group of maps generated by the reflections across these lines. So here's the picture for type A2 tilde. These lines here are the lines. This is the line H alpha tilde 0, H alpha tilde 1, H alpha tilde, and so on. We get a bunch of triangles here. These are the alcoves. Reflections across these lines generates an infinite group, which is called the affine Weil group of type A2. And it's actually kind of like an infinite symmetric group. So a couple of features which I wanted to point out. So first of all, the affine Weil group is in bijection with the set of alcoves. It acts simply transitively. So I can identify an alcove with an element of the Weil, affine Weil group. And I can also identify that with the center point of this alcove. So those are just sort of interesting or useful to talk about geometrically. So this point here is the origin. The fundamental alcove is this particular alcove right here. And the center point of this alcove is called, of course, Q. So I apologize, my apologies. But this alcove is A non. And so we can identify a point with it, with an element of the Weil group with what it is when applied to this alcove. The simple reflections in the Weil group are the reflections across these lines that are the borders of this fundamental alcove. And so that's all I'm saying. But this is just what I've said here. But the only thing to keep in mind is this bijection right there. Okay, and then I guess I've sort of said most of it, or part of this. The elements S1 and S2 are the same as in the finite Weil group A2. So there's a copy of the Weil group of type A2 as a finite subgroup. In fact, any two of these simple reflections generate a subgroup isomorphic to the finite Weil group of type A2, which is just the symmetric group S3. And so the Weil group also contains a group of translations. You can see here's a translation here. It's this alcove I translated by the group alpha 2. And in fact, the Weil group is a semi-direct product of the finite Weil group and the group of translations. So then the spiral elements, well, let's look at this element here, or this. If I take three of the simple reflections, so the simple reflections are the ones I described, they're the ones on the walls that are bordering the fundamental alcove. If I take I, J, and K be some permutation, I take SI as J as K, SI as J as K, SI, and I go on a certain length like this, that's what we call the spiral element. Now the group is very symmetrical, and it's enough to consider the ones which are 1, 2, 0, 1, 2, 0. And so let's call that W of L. And all of the spiral elements will have the same behavior, so we may as well pick these elements. We call this a spiral Schubert variety. And so basically, the theorem that we proved is that the lookup conjecture holds for spiral elements. If I take W as a spiral element, then we can detect X to be non-rationally smooth in XW with the lookup condition. So this is just reiterating the lookup conditions. So what are the ingredients of the proof? Because they're going to recur in the work that I'm going to talk about now shortly with Brian Boe. But the first ingredient was we wanted to describe this set of X that are less than a fixed W in terms of the W action on R2. We wanted to understand these integers Q by using this geometry, and we wanted to describe the NRS locus. So NRS means non-rationally smooth. The NRS locus is a set of, for us, it's the set of X's where X is a non-rationally smooth point. We wanted to describe this in terms of alcove geometry. So let me just explain quickly what this is. I'm going to show a couple of slides with some inequalities on them and so on, which you are meant to ignore, but I'll show them to you anyway. You're going to, however, the next two slides, I think you're supposed to ignore most of these slides. So this slide, you can ignore most of it. The point is we're going to define two regions in the plane by some inequalities. Delta L is a region which is a triangle. And actually, what we're really considering is the set of center points of alcoves which lie in this triangle. This is a triangle, or it's really the set of center points of alcoves lying in a triangle. We remove two of those center points, we get a smaller region R of L. So you can just ignore the precise definitions. But this is what delta L is, all the dots. The dots are the center points of the alcoves. Delta L, this is delta 7, I think, are all the dots inside this picture. And then R of L, we remove these two dots up here. And then the theorem was that if you're a spiral element of length L, then the points that are less than WL in the Bruhat order are exactly the points that are in this region RL. So it gives a geometric picture of the elements that are, this is W7. All these dots here are exactly the elements in the Bruhat order, which are less than W7 in the Bruhat order. And so then using this theorem, we can describe the set of X's such that where the points are non-rationally smooth. And we do that, it turns out this is a nice convex set. In fact, this is the set of X, this should have been a Q here, where X, the center point is in the smaller triangle delta L minus 3. And using these two facts, we can prove the lookup conjecture. So let me show you a picture here. This is a picture of the situation for W12, I think. So this big triangle here is the triangle of all the elements that are less than W for less than W12. This is W12 here. This smaller blue triangle is the set of all X's that are non-rationally smooth points. The colored triangles are the ones where Q is positive. In fact, it turns out in this case, Q is always equal to 1, which is not true in other cases. The white alcoves are the alcoves where Q is 0. Now you can see in this region of non-rationally smooth points, which is inside the blue triangle, there are lots of alcoves where Q is 0. What the lookup conjecture says is that you can reflect across a line while increasing in length and get to a colored alcove if you're at any white alcove, if you're inside this region. And that's what the lookup conjecture is for these spiral elements. Okay, so that's the picture. Okay, and this slide just says that. So are there any questions at this point? Okay. So let me move on. So how would we deal with type A2 tilde in general? So I will say that, this is very satisfying in a way, but on the other hand, the spiral elements are a very restricted family of elements of the Weil group, and we would like to understand all the elements of the Weil group. So how can we do this? So the first step, we would need a geometric description of Bruhat order. Now, again, this slide I don't really want you to read too much, but the point of this slide was to kind of say that in the prior work with Li, we kind of did this geometric description in what I would say is a not very efficient way. It was known that if you realize the Weil group in terms of infinite permutations, which you can here, it's described here very quickly, very briefly, there was a description of the Bruhat order in terms of infinite permutations. And we basically translated these infinite permutation description into this geometric description for the spiral elements, if W is a spiral. This led to a very lengthy kind of proof because it turned out everything depends on the coset of W modulo the finite Weil group, which has 6 elements in it. So you naturally, like many arguments, ended up having 6 cases. And so for a spiral element, this is manageable, but for an arbitrary element W, this turned out to be I worked at this with Brian at the start, it turns out to be very complicated. It's a very inefficient way to do it. In fact, it's not clear to me we could have done it. It's all impossible. So instead we had to, we reason more geometrically using the alcove geometry. Okay, so I'm going to show another slide with some more pictures about alcoves. So the first 3 bullets there are the things I already said. We have the roots, we have the hyperplanes, we have the alcoves. The new feature is I want to talk about root strips here. So let me just go on to the root strip here is going to be the region in between 2 of these hyperplanes. So let me just go to this picture and describe it here. So the region in between these 2 red lines here is what's called a fundamental root strip. And parallel to, it's a fundamental alpha 2 root strip. And in parallel to these are all the other alpha 2 root strips. They're the alcoves that lie in between 2 fixed hyperplanes here. And so there are 3 fundamental root strips corresponding to the stuff between 0 and 1, where it's 0 and 1 here. The spiral elements, it turns out, are exactly the elements that lie in one of these fundamental root strips. Now, if you look at the non-spiral elements, they're in the complement of these fundamental root strips, which naturally divides into 6 components, which we call chambers. Now, these look like they might be like Weil chambers, but in fact, it's not quite as symmetrical as it appears, because the odd chambers are actually different than the even chambers. You can see this there's several ways this will appear, but you can see this right now because the even chambers, there's an alcove here which touches the fundamental alcove. In the odd chambers, there's no chamber that touches the fundamental alcove. So even geometrically, they look different and they behave differently as well. But nevertheless, there are 6 chambers, and that's sort of how the going to be useful to us later. Okay. So I want to talk about hexagons. So let's say we have a non-spiral element W with some chambers. And again, in this slide here, I'm going to identify the valued element. I'm thinking of them in terms of the center points. Now, what I want to do is I want to define 6 elements which are going to form the vertices of the hexagon. Now, you don't really, I'll explain this procedure on the next slide. You don't really have to pay attention to it too much now, except that to understand that it's a quite explicit way of getting these vertices. It's not we just hope that we can get 6 vertices. Okay, I'll tell you how you get them on the next slide. So this is a picture for an element W. So here's an element W in chamber 1. So what I do with we get the elements W1 and W5 by reflecting across the walls of across the hyperplanes that are the boundaries of the chamber. And we get W3 by reflecting across the third of the hyperplane here like this. And we pick the closest, we pick the one at the hyperplane here in the fundamental strip that's closest to W. And then that gives us, so we have W, we have W1, we have W5. We get W2 by reflecting W1 across the blue line, and we get W4 by reflecting W5 across the blue line. And the way they're numbered is just so that when you go around counterclockwise, it's in order. This is W0 here. So that's this hexagon. And then the theorem is that the hexagons provide a geometric description of the Bruegel order. And the theorem is that if W is not a spiral element, then the set of X that are less than or equal to W is equal to the set of X whose alcove centers lie on or inside this hexagon, which is called X and HW. So they're the points in the hexagon. So this theorem actually encompasses, can be phrased to include the spiral elements, but what happens is that because the procedure for reflecting, some of the you don't do any reflection, so it actually degenerates to a quadrilateral. I call it a triangle on the previous slide, but in our new hindsight, if you look about it, one of the edges is really short, and it really should be thought of as like a quadrilateral. Another thing that happens is that the hexagons are more regular for W in the even chamber than for W in an odd chamber. I only have a picture of an odd chamber one here, which is a less regular one. But if you look at this picture here, you see, so this diagonal line is parallel to a root. So this is actually parallel to the root alpha tilde. So the center points that lie on a line parallel to a root we call a root string, as opposed to a root strip, which is a little so. But in any event, this vertex and the diametrically opposite vertex differ by a multiple of a root. That's not true for W1 and the opposite vertex W4. If you go down via the root alpha 2, you hit on this edge in the middle of the edge here. And that's also not true for W2 and W5. If you go across a root string with W5, you hit this edge up here. Okay, so the geometry is less regular for the odd chambers than for the even chambers. For the even chambers, everything is diametrically opposite each other in terms of a root string. It's not, however, a regular hexagon. Even though these things are opposite each other by multiples of roots, the hexagon is not regular even in that type even odd even chamber case. Okay, so now I want to talk a little bit about something. This slide is a little bit hard to understand, but maybe I'll just try and explain it simply. So there's a certain symmetry in the picture, which it's not apparent for anything I've shown so far, but it'll appear in a few slides later on, which I'll show some pictures. So suppose you have a simple reflection. Remember, there are only 3 simple reflections. And this simple reflection, so you take WS, it's either bigger than W or smaller than W. So suppose it is smaller than W. Then there's a relation, then the behavior of, with respect to this element, fixed element W, the points X and XS behave in an almost identical way. So we're fixing W and we're fixing a simple reflection such that WS is less than W. Now suppose we look at an element X. Well, XQ of WXS is the same as QWX. The point XB is rationally smooth, if and only if the point XSB is rationally smooth. The point is smooth, if and only if the point XSB is smooth. So they behave exactly the same way, and this is a kind of symmetry that we will be able to use. But it will help us understand the entire picture. So the elements that are the easiest to handle are the ones where there are two simple reflections going down, because they have the most symmetry. So there are three simple reflections. If W is not the identity, there's either one simple reflection or two simple reflections going down. The easy kind are where there are two simple reflections. We call those type 1. The hard kind are where there is one simple reflection. We call that type 2. Perhaps we should change our names, but in any event, this is where you give a talk and you realize all the bad choices of notation. Anyway, and by the way, there's a simple move for reflections on the left as well. To hear the reflection is multiplying on the right. In fact, if you do reflections on the left, that's what tells you whether you're in an even or an odd chamber. That's the difference, and that's why the even chambers are easier. The even chambers are the ones where there are two simple reflections going down. And so that's sort of the reason for the difference. Now, the next thing is that we want to understand the locus where QWX is non-zero. I want to organize the alcove centers into shells. So let me just, instead of looking at this slide, which is just a verbal explanation, let me show you a picture which will make it completely clear. So here is the hexagon again for this particular element W. The elements, so the alcove centers on the edges, on the outside of the hexagon, are the zero shell. Now I can look at the alcove centers that are on the edge that is, the closest possible to the alcove, to the edges on the outside of the hexagon. In this case, it's the edges that are on this root string. So I go around and I look at the ones that are the next closest to the outside of the hexagon. Those form the one shell. I can go one further and form the two shell. I can go in like this, and I can organize the situation by shells like this. And if one can write down a formula, just a bit more formally, but in this case, we see that the zero shell is the black, is either in black, the one shell is in red, and the two shell is in orange. Now, again, what we should really be thinking of, they're not all on this picture, but really the points on the shells are like the dots in the center, or the alcoves that goes through. They're the vowel group elements that correspond to that. The only dots that are on this picture are the ones at the vertices. Okay, so here's a theorem that describes, based on this, we can describe a locus where Q is actually equal to 0 for a non-spiral element W. And so for simplicity, I'm just going to do this for a type 1 element. The type 2 element is similar, but I think the type 1 is probably enough for us to do in this talk. So the point is that there's one particular kind of element, which is if you take an even length spiral element and you hit it with one simple reflection and go up, you get something where Q is 0 for every point inside that. It's a strange phenomenon. So let's suppose we're not in that case. So there's this one particular case where all the Q's are 0. Let's suppose we're not in that case. If we're not in that case, then if Q is 0, the only possible points where Q is 0 are on the 0 shell, the 1 shell, or the 2 shell. Those are the only points where Q is equal to 0. But Q is not 0 at all of those points on those shells. There are certain points which we call special intervals on the outer shell where Q is non-zero. And then any point you can get from these outer shells by hitting it with a simple reflection that goes down from W, or the group generated by that, you get Q to be positive as well. And so I'll show you a picture which will make this much more clear. But here, the simple move is actually appearing in this part here, because here we're using the fact that these Q's are all the same when we hit it by reflections like this. So let me show the picture here. So what are the special intervals? intervals. Okay, so these only occur if W is in an odd number chamber. So let me just show you the picture and not focus on this slide. So here's the picture here. So we're in an odd number chamber. So here there's a special interval in red and a special interval in purple. And how do we get these special intervals? Well, as I said, these points are not diametrically opposite the other vertices. So if I look at W4, I go up, this is going to hit, it's not going to hit W1, which it would if the hexagon were more regular. It's going to hit this edge at a certain point here. If I start off at W5 and I go all in this direction, again, it doesn't hit W2, it hits this edge at some other point here. If these depending on the way the hexagon is configured, these orange lines, it looks like in this example, they cross in the interior of the hexagon. They don't have to cross in the interior of the hexagon. It depends on the shape of the hexagon, which depends on where W is located. But if they do cross, then where they hit this edge here, the alcove centers on this region here form what we call a special interval. And we do the same with these two other edges here, and we get this special interval down here. Now the points on the outer edge, which are in the special interval, satisfy Q equal to 1. By applying all the simple reflections which go down from W, this is a type 1 W here. There are two simple reflections which go down from W. Applying the two simple reflections to these elements, I get a little hexagon here, and a little hexagon here, and a little hexagon here. And these elements also satisfy Q being positive. And then Q is equal to 1 in that case. And this is how these are the elements where Q is equal to 1 in the outer three shells. And on the outer three shells, otherwise Q is equal to 0. In fact, the reason you see the outer three shells occurring together is this little hexagon. There's these hexagons around the outer edge, and the outer three shells all have the same behavior. In fact, it's for a type 1 element. Okay, so anyway, it's a somewhat, it's a very pictorial kind of statement. And so anyway, this is just same with that one. So then using the description of this locus where Q is equal to 0, we prove that if W is a non-spiral element, then the following holds. So suppose you start off with a given X. Now what we expect is that as Y is less than X, we expect the singularity to get worse. And so what we think is that if QWX is positive, ideally QWY would be positive too. It's the failure of this to always happen that leads to the complications with this Carrell-Peterson criterion. If when we start off with QWX, if QWY were always bigger or always positive, QWX is 0, then there would be no lookup conjecture. Because if this were positive, then this would be positive. And once I hit a non-rationally smooth element, the first non-rationally smooth element, Q is positive. Any element below that, Q would also be positive, and therefore there would be the lookup conjecture, only the trivial case of a lookup conjecture would occur. So this theorem says that if it's a non-spiral element, only the trivial case of a lookup conjecture occurs. You start off at a point where Q equals 0, you get smaller, where Q is positive, you get smaller, you go from X to Y by getting smaller, Q remains positive. So there's nothing else to do there. And so the proof actually identifies the maximal elements where the Q is positive, and so those are the maximal non-rationally smooth elements. So in a sense, we're getting a description of the non-rationally smooth locus as well. And then since the lookup conjecture this basically says that this proves the conjecture that Wenjing Li and I made a long time ago, which was that for the only cases where the non-trivial case of a lookup conjecture occurs are the spiral elements. This proves that. For non-spiral elements, only the trivial case occurs. Since the lookup conjecture is actually true for spiral elements, this proves the lookup conjecture for type A2 tilde. Okay, so that's the lookup conjecture. Okay, so are there any questions?
Yeah, sorry, I'm still confused. All right, so this is for affine value.
Yes.
And this relates to the flood variety for the test study?
Yes, for the test group. Yes, that's right.
So what is the status of the lookup conjecture, like rank 2 groups, like in the regular value?
It's true for all finite values up to rank 6.
Up to rank
That was
6.
checked by computer.
Okay. So like for B2 tilde.
Well, for B2 tilde, And G2 tilde, some computer evidence indicates that it's true. And I'll say a little bit more about that at the end, but we don't, I mean, it seems like all the methods we're using for A2 tilde will work for E2 tilde and G2 tilde as well, I expect. So we just haven't done that yet, but I think actually that will probably be the next thing we do after this. But it was checked, I think, but via computer it was checked for all elements W up to a certain length in those groups. So it's very likely true. Okay. Any other questions? Okay, so, well, you might think I'm done since I got to the lookup conjecture, but no, in fact, I have more, so I made some more slides. So the next thing one might wonder about is the locus of smooth points. So if a point is smooth, then it's rationally smooth. Smoothness actually refers to this relative cohomology with integer coefficients. Now, for simply placed groups of finite type, the reverse implication holds, and smoothness is actually equivalent to rational smoothness. So again, one might think in type A2 tilde that this would be true as well, but it turns out not to be true. Smoothness is not equivalent to rational smoothness. But then this raises the question, how can you tell if a point is smooth? So these integers qxw do not distinguish between smoothness and rational smoothness. However, Carrell and Kumar proved that there's a more refined invariant called the equivariant multiplicity, which actually, in hindsight, comes from equivariant cohomology, which does detect smoothness. So let me tell you what that is. So the equivariant, let's take an expression for W, a reduced expression for W. So this is a list. So SI1, SI2 up to SIN are simple reflections which multiply to W. And it's the shortest possible list of reduced expressions. That's called a reduced expression. So a sub-expression is just a sequence where I either take the reflection or I take one at that point of the reflection. So I just, in a sense, I throw out some. By taking one, in a sense, I'm throwing this element out, since it's a sub-expression. And then S of X will be the set of sub-expressions of this S multiplying to X. And then the equivariant multiplicity is EWX, which is, the formula doesn't matter too much for us, but the point is more that it's a formula which is, it's a rational function, and it's obtained by enumerating over all the reduced expression, all the sub-expressions of this original expression S, which multiply to X. And I have to hit these roots here. Now, the only thing to keep in mind in this setting, which is something that I have kind of glossed over entirely, is that the Kac-Moody group has its own set of roots, which are not the roots alpha 1, which are not just the roots alpha 1, alpha 2, and alpha tilde. And in this setting here, we really have to be dealing with the roots of the Kac-Moody group here, which is something, it's not too hard to deal with. The point is that, if beta is a real root of the Kac-Moody group, the reflections in the Kac-Moody sense amount to these reflections here for some integer n. And so you can determine this set of, this set of psi is a set of reflections in the Kac-Moody group, which are less than W. And that's basically can be determined by looking at the set that we were considering, the reflections would stay less than W. So that can be determined using the hexagon. And in any event, Kumar proved that if X is less than or equal to W, then the point is rationally smooth, you get a condition which is very much like the Carrell-Peterson criterion, where the equivariant multiplicity is a constant over this fixed product. This product is a fixed product. If it's rationally smooth, this product has the length of W roots. It's just a product of roots. It's a predictable product of roots. And it's some constant over this predictable product of roots. And the constant has a predictable sign. The sign of the product, it's positive up to this sign that can be predicted. The point is smooth. In fact, you only need to check it at that one point. And if you get plus or minus 1 in the numerator, then it's a smooth point. So that's what Kumar proved. So Brian and I wanted to go on and determine the smooth locus. So we had to do some reductions in this case. We can describe the Q's for any x less than or equal to W, but these equivariant multiplicities are much harder. However, to determine the smooth locus, we only need to do this for a small number of x's. So first of all, we only need to determine, sorry, this is a typo here. So when I was proofreading my talk this afternoon, I didn't get to this slide, so I didn't get to fix this typo. But we only need to we only need to focus on, this should be an equal sign, not a greater than sign. What we really need to do is, we already know the rationally smooth elements. And particularly, we know the elements where Q is equal to 0. Any element where Q is positive is already not smooth. So we never have to look at those points at all. We only have to look at the points where Q is equal to 0. And we have to determine which of those are smooth. Now, smoothness or being singular is a closed condition. So if y is smaller than x and x is not smooth, then y is not smooth. So once we found a non-smooth x, we know that everything smaller than y is also not smooth. So we can reduce it there. There's also a version of the simple move for equivariant multiplicities. So we can use that to simplify our calculation. And there's another move, which Brian and I call the setup move, which can also be employed to reduce the number of elements. So you can do all these reductions to say that, in fact, there's only, it turns out, after all this stuff, there's only a very small number of elements that you need to determine, to calculate this equivariant multiplicity for. I think it's typically 4 elements you can get it down to, which is then sort of manageable. And so the following, so here's a theorem describing the locus of smooth points. So if W is not a spiral element and x is less than W, then x is a smooth point if and only if x belongs to one of 6 alcoves near one of the 6 vertices of the hexagon. And these near alcoves can be described very precisely. So let me explain this on the next slide for a type 1 element here. So here's a W of type 1. There are 6 alcoves here. Now, these 6 alcoves are actually all smooth points. It turns out, I mean, the 6 vertices. It turns out one needs to show that. That's not obvious. The simple move then says you can take, there are 2 simple reflections going down from this element, and they generate a little hexagon of alcoves. When you apply those reflections going down, you get a little hexagon of alcoves at every vertex. And those points are also smooth. And this is the complete list of smooth points in the Schubert variety. So it's a much smaller, in this picture, the hexagon is rather small. So, it looks like there's a lot of smooth points, but as the hexagon gets bigger, there will only be a relatively small number of points clustered around the vertices that are smooth. For a type 2 element, there are also 6 elements that are smooth around every vertex. They're arranged in a slightly different shape, which I unfortunately don't have a picture of. I think Brian was thinking an appropriate name for this shape, and I'm not quite sure what he's landed upon. Okay, anyway, so we have the complete description of the locus of smooth points. And so let me just say, I'm just if you're interested, for spiral, so Wenjing Li and I actually worked out the smooth loci for the spiral elements. And this is the smooth locus for a length 11 spiral element. So for spiral elements, it's actually a somewhat similar picture, except that some of the elements aren't less than equal to W, so you don't get all these elements here. I should say that in this other picture here, if the 2 hexagon vertices are close to each other, these 6, the little 6 elements next to each vertex can overlap, so you might not get 12 elements there. But in any event, so this completes the picture for type, A2 tilde. And again, this is when I said understand the smooth locus, I meant come up with some kind of description like this where you can sort of see what the set of points that are smooth or rationally smooth are, as opposed to having to employ some test like a Kazhdan-Listing polynomial, which would be difficult in any set. So let me just mention that there's a couple of future directions that are, I think, we were planning to look at. So again, as you were asking, Dan, I said types B2 tilde and G2 tilde should be amenable to very similar analysis. Now, type AN tilde is actually surprisingly daunting because first of all, you're going to be looking at Rn instead of R2. So visualization, of course, becomes much more difficult. The geometry is going to be more complicated. In type A2 tilde, the only possibilities were either there's one simple reflection going down or two simple reflections going down. But in type AN tilde, you're going to have any number of, you could have all kinds of configurations of numbers of simple reflections going down. So that will be more complicated to analyze. So the results from type A2 tilde should provide useful guidance, but again, it's really doesn't seem completely trivial to me to go from type A2 tilde to type AN tilde. It actually seems rather difficult. But this is what we hope to do. And then finally, when Brian and I were thinking about this for finite model groups a long time ago, we weren't really thinking in terms of this geometric picture of alcos and stuff like this and so on. And so I have some hope that going back to thinking we can have a more geometric picture of the locations of the elements of the model group that can be possibly useful in revisiting the lookup conjecture for finite types as well. So I think this, hopefully this may give us some insight into the finite types. So anyway, that's all. So thank you very much. Yes.
Maybe on the lines of your last point, so your solution type A2 made me wonder if there's a connection with casuistic cells somehow. The spiral elements of casuistic cell, I believe.
They do. Interesting. I see. Interesting. So it would be interesting if there's some. Well, I mean, in a sense, rational smoothness is connected with like casuistic polynomials, of course. So there should be some. It's good. That's interesting. I had not thought.
I have another one. So on the surface, the rational smoothness is a question purely about the about the Brewer interval, right? I mean,
yeah,
it's a geometric motivation, but it's. I mean, the lookup conjecture just asks if this interval condition can be checked at the bottom of the interval.
Yes, that's right.
Have you thought about this for cluster groups that don't have any geometry associated with it?
We've thought about this in the sense like the question has come to our minds, but we haven't. I don't think we've seriously investigated it yet. But I mean, I would sort of expect it to be true in those cases as well, actually, because the kinds that in this fairly recent work of it was shown by Elias and Williamson that the casuistic polynomials, for example, are positive, have non-negative coefficients for such Coxeter groups. They exhibit a lot of the same kinds of behavior. So I would expect that it would probably be true in those cases as well, but I don't.
Yeah, so for the conjectural there's an interpretation of the
Yes, equilibrium. Yes, the local intersection cohomology.
I'm just thinking
Yes. Yes.
So do you think any of that technology can be used here? Because we have the alpha geometry, we have the reflection, and we have a lot of representation there.
Well, that's an interesting. So in fact, although I should have put this on the slide. I think it was on one version of my slides. So in fact, the Carrell-Peterson criterion had actually appeared in earlier work of Janssen on highest weight modules.
Yes.
In fact, so it really should be called perhaps the Carrell-Peterson-Janssen criterion. In fact, and so there is this connection, but I don't know how that could be. I don't know enough about that to know how that can be used to prove the lookup conjecture in a sense. But it would be it's sort of interesting. Maybe it would be interesting if there were. I don't know. Is there like a?
So it's like the alpha geometry. One of the big tools is the translation functions, and we're like translating on top of that across algorithms. So I'm wondering if that has anything to do with.
I don't know, but it's just maybe this is something having to do with this synonym of words. But if you look at this picture fact, for the spiral elements, if what turns out to be true is, in fact, if two elements differ by a translation in the Weil group, then in the spiral case, then their Q's are the same in fact. So that was actually one of the key things we used to. This is actually a rather complicated looking picture, but it turns out that in fact, if you prove that these two elements they differ by a translation by a root, and therefore the Q's are the same, and therefore that you want that actually restricted the number of elements one needed to calculate. But as I said, so that meant you only need to consider the Weil group modulo this group of translations, which is there are 6 cosets to the Weil group, and hence that was the painful 6 cases. That was the manifestation of the painful 6 cases I was referring to earlier. I don't know if this is just a coincidence of terminology with translation, but this geometry did appear. I think somehow this geometric picture is somehow, it's interesting. I think maybe it would be interesting to see if one could get a bit more. I mean, I think the lookup conjecture is probably true. I mean, it seems like there's a good deal of evidence for it now, but it's I don't really quite know the reason it's true. So. Yes.
Do you have a piece of this?
Pardon me?
Do you have a piece of this?
You mean in characteristic stuff, the locus that's swinging. I don't know what you mean by the piece of the locus.
Like if you replace the field Q.
Well, I mean, the arguments that we're using are basically combinatorial. So in the sense, I mean, except actually I would say in equivariant multiplicities calculations, that's sort of at the end of the paper. I mean, I didn't, the equivariant multiplicities calculation is somewhat combinatorial, but you are looking at, you're enumerating reduced expressions, because in a sense it's combinatorial. So I don't know if one had a combinatorial description of the P-smooth locus or the P-rational smooth locus, then one could try and attack it using the methods. And the Bruchau order is going to be the same, and that's probably the main thing. But I don't know if there's like the Carrell-Peterson criterion, for example, or anything like that. I also don't know. Like this Kumar's criterion for smoothness or rational smoothness. Like I'm not sure what fields that's true for. So I mean, that's a good question, but I don't know.
Just a random question. Is there a natural class of interesting points between the rationally smooth points and the most general points? Is there something in between? Or like here you say it's like rated characteristic whenever equal to 1, but other equals a spatial.
Well, you can. I don't know exactly, but for example, I mean, one thing that you could do is in this Kumar. I would say that I think that that one thing that one could consider is like this Kumar thing. There's this numerator here. One could consider the points where the numerator is, one can stratify this in a sense by the points where the numerator is less than equal to 1 or less than equal to 2 or less than equal to 3. I don't know if those strata have any sort of geometric interpretation, but I think there are sort of classes of points where where the numerator varies. The numerator is measuring something, but it's hard to say what exactly it's measuring. I mean, it's in fact what happens in these examples. What happens is that in some cases, like the numerator is like the actual multiplicity in the sense of algebraic geometry, but in general, I don't think it's true that or known that equivariant multiplicity the numerator would be the same as like the multiplicity in algebraic geometry. But so I don't know. That's a good question, but that's I mean, one can look at various kinds of invariants and of these things. I mean, Lustig actually, I will say, it would be interesting to look at the work of Lustig because he's always looking at these kinds of stratifications and he's like throwing in additional points like these special pieces or this or that. And so it's possible that, like somebody like Lustig has considered some kinds of intermediate types things that would be very interesting.
There's no further questions. Let's go ahead.